Hi guys, hope it's going well. This is our fourth lesson, and it's kind of a departure from what we were just doing with trig identities. But before we get to the lesson, why don't we do a couple warm-up questions so you can try them out before you look at the solution. These two aren't so bad. If you have any questions about them, just let me know, but you can go through the solutions here. I don't think they're so complex that I need to discuss it thoroughly. So as I said, we're going to get into the actual function part of this lesson, and it's all about what are called periodic functions. And this is when we start dealing with what sine, cos, and tangent look like in graphs. And before we get to that, we're going to just look at how you can have a whole bunch of different things in real life that are periodic functions. And there's some vocabulary and some just basic understanding that we have to have of them before we move on to the sine, cos, and tan stuff. So a periodic function, if we just state a definition, so it's a function that has a pattern, but it's not just a pattern, it's a pattern of y values that repeats. At regular intervals. And these regular intervals are really referencing the x values, or the domain. So it's a function that has a pattern of y values that repeats itself over and over and over again, basically. So, of course, why not GIF it? And so if you think of, there's lots of things in real life that follow this pattern. Populations of animals follow cyclical patterns, periodic patterns. I gave the example here of the electrical impulse of a heart. As long as the heart, you're at rest, it's going to remain the same, and you get what looks like a periodic function because it just repeats itself, and the y values don't increase, they just stay the same. Here, it's kind of a spoiler alert. On the right here in this green, I'll just highlight it here in yellow. This is the unit circle. And if you were to graph all of the angles for sine and cosine, and later we'll see tan, it starts to look like this stuff. So the blue being cos and the red being sine. So one of the applications you can see from this is actually, if you were to ride a Ferris wheel, imagine you're this green dot here. If I just stop it, green dot here. If you're on that Ferris wheel, you can think of your height going up, and then it starts to come down, and then you reach your lowest point, and then you're going back up, and so on. That's kind of an example of when this happens. In physics, for those people who have done physics, some of this will be slightly repetitive, but I think it's good to do again. But in physics, there's so many things that follow periodic functions, like electricity currents, wave motion. So anything to do with energy is going to follow periodic function. And so first thing to do, bye-bye GIFs, is which of these are periodic functions? So if you look at the first one here in A, it says we've got this obvious pattern that's repeating itself, but it's not periodic. So it's not because the y values are changing. And in this case, they're increasing. So we have something that's a repeating pattern, but it's increasing, so it's not a periodic function. Next one, hopefully you see, it's an odd pattern here where it looks like we've got w's going on, but yeah, it's a periodic function. And so the y values repeat themselves. And it has to happen over the same interval. So like if I was to follow along, if I highlight this, so let me start here at the top. If I follow along, from here to here, it looks like that's the first W shape. So I'll just re-highlight that. And so it starts at 0 and it ends at 8. The next one should be the same length. So like if this is from 0 to 8, that's 8 units. The next one should also be 8 units. And so it should finish at 16, which it does. And so that's a periodic function because it has a regular interval where the y values repeat themselves. Okay, some more vocabulary. In periodic functions, we say that one complete pattern is called a cycle. And so the cycle, the length of one cycle, or the horizontal length of one cycle, is what's called the period of the function. So like if you think of the moon phases of a 28 days, the period would be the 28 days, and the cycle is one repeating pattern of the moon shapes, or whatever you want to think of, until you get back to the full moon, if that's where you think where the cycle starts. But what's weird is like if you look at this example that I had with the W1, if we call this the beginning of the cycle, so right here where I've got that red dot, so you can call that the beginning, which looks like an obvious point to start with, but it doesn't necessarily have to be. You can start if I get rid of this, oops. If I get rid of that, let me fix this. You can start this function, let's say I started here. So down here. I can think of it as going like this until I get back to where I started. And notice I can tell where I'm going to start again because it's when I go up for this big curve up. And so you can start wherever you want, and that's kind of a challenge. And so you have to figure that out. So you can figure out the length of one cycle. So if we stick with what we had before, so just the W shape seems like the most obvious. So the period is the distance from one part, the beginning of the cycle, to the other part, which is the end of the cycle. So this gives me my period. And so in this case, you can take either the end minus the beginning, and so I've got 8 minus 0. So my period here at us is 8 units. So pretty straightforward. And you can always double check with the next length of the cycle, and it should be the same. If it's not, then it's not a periodic function. Okay, so some of the things we can do is use function notation to figure things out on the function. And so this will be going back to what we did a long time ago. If I write f at 4, so remember this is like f, the function at the value 4, it means find y when x equals 4. That's basically what it's saying. So if you look on the graph and we go to, I'll do it in a different color. If we go to 4 for x, so here, and I go up, here's my value, my y value at that, which corresponds to 2. So f at 4 equals 2. Let me write that in. So f at 4 equals 2. So I'm just taking it from the graph. If you do the same thing, you can try this. F at 10 here is going to be 0. So the y value there is 0. The next two here get a bit trickier. So f at 20 and then f at 66. So if you look at your graph, the problem is it doesn't go to 20 and obviously it doesn't go to 66. So what we have to do is we have to predict these. And we're going to predict them if you think because it's a repeating cycle, we can predict using the period. And so knowing that the period length is 8 units, basically, if you think here first at f at 0, I get a y value of 4. If I go one period length away from 0, so if I do f at 0, what I should get is the same as f at 0 plus 1 period length, or f at 8. And that should be the same as the next time it occurs, which is f at, let's say, 8 plus 8, which is another period length away. All of those should equal to the value of the y value 4, which it does, and that's these points here. And so what you can do is you can say, instead of f at 20, I know that f at 20 is going to be the same as f at 20 minus a period length. So this is where I subtract a period away from it. So f at 20 minus 8 is really the same as f at 12. So that I do have on my graph. So I look at f at 12. So f at 12 is there. And I get a value of 2, like that. So you're just predicting using what's happening with your period length. So f at 66, what I need to do is subtract a whole bunch of periods away. And knowing that the period length is 8, there's multiple answers you can get to this. I basically want to get into where I can see it on the graph. My graph goes from, looks like -4 all the way to 16. So what if I just subtract 8 periods? So this is like subtracting 8 periods away. So what I get is f at 66 minus 64. So it's like I've gone back onto my graph, and that obviously is just going to be f at 2. 66 minus 64 gives me 2. So I go to f at 2, and f at 2 is 0. And so you're using the values that are there in order to figure out using the period length and go from that. So not too bad, but good to do. So if you look at this one, it says, just to practice another one, what's the period of the following function? And so you can try this if you want, so just press pause. So again, you want to pick anywhere. Like if I was to pick somewhere that seems logical, I'm going to start right at 0. And so I go all the way like this. Notice I get back to 0, but the function doesn't repeat itself, because if it did, it would go like this, go up, but it doesn't. So I have to keep following until it starts to go back up. So here, my period length is going from 0 to 6. So my period equals 6. So a few other, and this I think is on the same page for you, but a few other vocabulary terms we need to know on this. One is the max, and that's pretty self-explanatory. It's the largest y value that the function reaches. And the minimum is the opposite, it's the smallest y value that the function reaches. The amplitude, this I think the physics people will know, the amplitude has to do with the vertical part. So like if I go back to this one here, like if you ever played a musical instrument and you've got it plugged in, or if you've ever had any sort of amplification where you see visually, and this used to be big in the 80s, to walk around with these big massive amplifiers that showed you this amplification. It's the vertical distance of that function. It's the same thing with waves in the ocean. They talk about, wave height. That's the amplitude. And so the amplitude is half of that, half of the difference between the max and the min. So it's vertical. And when they give wave heights on the ocean, if they say it's 2-foot waves, that means that from the middle of the wave to the top is 2 feet, and from the bottom of the wave to the top would actually be 4. So as a formula, we say the amplitude is equal to the max minus the min divided by 2, like that. So pretty easy. Okay, so you can try these out. Not, I'll take these up, but you can try these out because this isn't super hard. There is a little quiz for you to try at the end of this, but try these out, see how you do, and I'll go through them. So this one, first one is highlight one cycle of the graph. So I'm going to pick somewhere, I think, easy. So let's say here, and I go till I repeat. So from here to here. So that's my period. And it says state the period. So assuming these ticks are 1 unit, so I go 1, 2, 3, 4. And then similar for amplitude, I've got a max here of 2. And I've got a min of -2. So my amplitude is going to be 2 minus -2 divided by 2, which is just 2. Next one's a bit trickier for the period. So I would definitely try this out before you watch what I do, but again, you can pick any point. Obviously, you want to pick something that's on the grid nicely. But if I pick here, I go and do this kind of mountain shape. And it looks like I'm done, but notice, oops. Looks like I'm done, but notice here, it doesn't go back up that full mount. So that means I'm not done one cycle. So I have to include this little part here, and then it starts to repeat itself. So from here to here is my period. Again, you could pick elsewhere if you want. Maybe you pick right here. If I do this in a different color. So I go here, and I know that that's where it's going to stop, and you should get the same period. Either way, I'm going from the first one here, -7 to +1. So that's going to be a period of 8 units. I should put units here. And my amplitude's going from 4 down to -2. So I got 4 minus 2 divided by 2. So I end up with 3. And so not too bad. And the next part, it says find f at 13. And I think just f at 13 for A. So in this one, we'll look at A. I'll just write that in. So f at 13 obviously is not on the graph, because if we count here, this is 1, 2, 3, 4, 5, 6. So this is just 6. So I need to subtract some period lengths. So I'm going to have to do f at 13 minus, let's say we do 2 times period length. Period length is 4. And if you don't get far enough along, you can keep subtracting more. But this becomes f at 13 minus 8, which is f at 5. And I can figure out 5, which is, let me just double count, 1, 2, 3, 4. Oh, this was 5, oops. So I'm actually down here at -2. There we go. Next one, same thing. I've got f at 34, but that's way off the graph. So what if its period length is 8, so what if I do 4 of them? So 8 times 4, which is 32. That definitely gets me to a spot on the graph, so f at 2. So if I go to 2, is that right? Yeah. I get the value of y being 1. And so again, just so you remember, like, this is really the point, which is going to be 13, -2. That's really what we're finding. Similar here, I've got the point for x, 34, and the y value of 1. Okay. So why don't you try those and go into the work stuff, and